Many thanks, Andreas, for your kind introduction, and thanks to the organizers for inviting me. And we set up everything. So I decided, despite of the bit frightening title, to focus today on some logical issues and also to some, maybe novel forms of doing reverse mathematics. But just here a general introduction or propaganda slide. So proof mining, as this type of applied proof theory often is called, I view this as Hilbert's program in action. So Hilbert had this idea that, in principle, it should be possible to eliminate non-effective, ideal, infinitary, whatever principles in proofs of concrete statements. And so, in particular, he focused for good reasons on the consistency program, because if consistency could be proved of a system by finitistic means, then every pi01 sentence which would be provable in this respective system could be provable in this finitistic setup. And however, he had himself already the broader goal of extracting information from proofs. So if you have a proof of an existence statement like the Hilbert's Nullstellensatz, in Hilbert's own school, Grete Hermann, as a student of Emmy Noether, extracted bounds from that proof. So I think that Hilbert already had this broader goal, although it was Kreisel in the 50s who actually launched this reorientation of proof theory to apply proof transformations not only to non-existing proofs of uninteresting statements like 0 equals 1, and a consistency thing, but to existing proofs of interesting statements. So why not, for a change? And so during the last 20 years, this has resulted in many new results and in various areas of mathematics, which you see here. And for us, we talked about yesterday, logicians, which journals should they publish in and so on. For this type of research, of course, the gold standard is if you claim you have an application in ergodic theory or in optimization, that then the paper is accepted in the best journals of these respective areas. So there's no logic editor pushing the paper. So that actually happens here in most cases. Now, it has been sometimes criticized, the original version of proof mining called unwinding of proofs by Kreisel has been sometimes criticized, for example, by Pfefferman as kind of ad hoc. So if you're lucky, you get a result, you claim it was an application of logic. If you're not lucky, well, then you move on to the next example. But this is not quite true. Actually, there are general logical meter theorems which guarantee and explain these findings. And this typically goes, in these two developments, the development of new meter theorems and and to get new applications, this nicely interacts. So you may have a logical meter theorem, you search for applications, you have applications, then you get excited about this area of mathematics, you do further applications because somebody in optimization suggests you should do this. It's not actually supported by the meter theorem, but let's do it anyhow, it works. Then if that happened a couple of times, then you might rethink your logical foundations and say, maybe I can incorporate this piece of mathematics directly in my framework and I can explain why this works nicely. And you will see an instance of that. So here are a couple of papers doing this. Now I come to actually this talk. It turns out that about, I mentioned here some 200 papers. I think meanwhile it's 250. There's a nice bibliography maintained at Nicolas Pischke's webpage. So about 90% of those use actually a device which I introduced in 2005, namely to add to the standard systems we use, let's say second order number theory, or as I use, because these developments are mostly based on functional interpretations, so some modern versions and extensions and variants of Gödel's dialectical interpretation. So you use actually finite typed system, not just second order system. But to add to those, to hardwire into the framework abstract metric structures, like an abstract metric normed Hilbert space of so on. And what is the point? Because we don't want to talk about spaces in the way the reverse mathematicians do. We don't want to say the way we talk about a Banach space is by saying, it's actually the completion of a pseudo blah countable structure, because in this way we smuggle in separability in the very setup of the thing. Now, why should we not want to do this? Most foundational approaches, Bishop, constructive mathematics, Pfefferman's explicit mathematics, reverse mathematics, they're all in one way or the other say one should avoid non-separable spaces. As Bishop says, it's pseudo-generality. We are not avoiding separability because we are interested in non-separable spaces, but we don't want to clutter the computational content of a proof. And if the proof does not use separability of the structure, the bounds will be much more uniform than otherwise. Now, if your formal system forces you to introduce separability, although the proof doesn't, then you destroy this feature of the proof. That's the main thing. Okay, so 90% of the things do this, and then we can actually do without compactness. So basically, metrically bounded structures behave as if they were compact. Now, we know this in a sense from model theory, from continuous model theory. You have the same phenomenon, or as the functional analysts would say, well, this is what happens in the ultra product of such a structure. In some sense, we replace ordinary V-Königs lemma type compactness by this ultra product type compactness. But we do this completely finitistically and constructively and not using ultrafilters. Now then one works, so one of my favorite systems is here these Peano-arithmetic and finite types. So that's an extension of Gödel's T by classical logic. And there are technical issues, actually very important issues about how to treat equality. And we always want, as mathematicians do, treat equality as extensional equality. So two functions are equal if for every argument they give equal results. If you do that, if you then state the equality axiom saying equal things should be respected and translated into equal things, this becomes a strong axiom, namely an extensionality axiom, and it has been long observed that that doesn't have a functional interpretation. Now, this is sometimes presented as a kind of problem or drawback of the Gödel interpretation, but it's actually not. Because it's a substantial mathematical issue. So I sometimes claim there's only one principle in mathematics which doesn't have a computational interpretation. It's not Zorn's lemma. It's the extensionality axiom. And the axiom of choice and Zorn's lemma and so on, they are only strong in as much as they involve extensionality. And so that's actually a serious thing. And my talk will about extensionality and its reverse mathematics. So in the base system here, we only allow a quantifier-free rule of extensionality, which you'll see in a minute. And then we hardwire here this kind of abstract structure, which we cannot represent because it's not separable. And so we just hardwire this as a new type in the system, and we build the finite types on top of these two, the natural numbers and X. And here I just depicted the case of a norm space. Many structures, geodesic spaces, cut zero spaces, cut kappa spaces, whatever you, uniformly convex spaces, uniformly smooth spaces. Lots of structures can be done. So this, by the way, suggests already a new type of reverse mathematics, namely to talk about abstract things. You have, let's say, in a ergodic theoretic statement, suppose X is a Hilbert space, not a separable, a Hilbert space, and you set up some ergodic iteration, then this converges weakly or whatever to some stuff, to some average. What principle is that equivalent to some axiom on top of? That's a new type of reverse mathematics, with abstract types. But also, I think one can often and should, and I've currently a master student who hopefully does, he hasn't progressed very much yet, but he hopefully does, to translate results, very complicated results we found in proof mining, to recast them as ordinary reverse mathematics results. So if you say, now my space is actually separable, and I don't have in general abstract closed convex subset, I have an effectively closed set with a code in the sense of Simpson, then what does this original result tell me. It's not straightforward because on the one hand, we are here much more general. If it works in the abstract, you might think, well, then it works in particular in the special case. But in the abstract setting, things are represented, as you will see, in an intentional way. And for example, to be a member in the convex set is a quantifier-free statement. Whereas if you say you're a member in an effectively closed set, there are quantifiers involved, and that's, depending on what type of representation you have, this already may trigger arithmetic comprehension. By the way, it's also, I think, sometimes reverse mathematics could be misleading. It turns out many results which are equivalent over such a system to arithmetic comprehension are only so because you say, because in the reverse mathematics you say a point only exists if you have a fast sequence converging to it, fast converging. But in numerical analysis and optimization, you often have algorithms actually converging to your point in question. And the fact that this algorithm is Cauchy, and that then the limit, if it exists, has to satisfy the property, usually is just equivalent to sigma 1 induction. Okay? And then the only use of arithmetic comprehension is to say, if I have a Cauchy statement, I scolomize it, I get a Cauchy rate, and then with that I can speed up my thing and I get the limit point. So it's a one-line application. So you have already your result. For all intents and purposes, the mathematician would say you're finished, the result is proven. But you say, no, for the reverse mathematics, I need the last line. And therefore, by arithmetic comprehension, the limit exists. So only that thing is arithmetic comprehension. So I think one should focus also on the reverse mathematics of Cauchy statements. What is needed to prove the Cauchiness of the algorithm converging to this point? When analysts have an algorithm converging to a point, they call this a constructive proof. So for example, this. Bragg proved in the 70s using Zorn's lemma that sunny non-expansive retractions exist, in certain conditions. And then much later it was proven that certain very complicated iterations strongly converge to that. The title of that paper is a constructive proof of the existence of sunny non-expansive. So for all intents and purposes, it's now algorithmic. Now, of course, sunny non-expansive retractions are generalizations of ordinary projections in Hilbert space, and we know by Avikat and image this already implies arithmetic comprehension, so it cannot be better than arithmetic comprehension. But from work we did, that the Cauchy property can be proven without any comprehension, actually we show it's also not worse. And I think it's misleading to say whenever you use such projections, you invoke arithmetic comprehension. So anyhow, so that was about this last. Sure. They don't even understand what you're talking about. Even numerical analysts claim they don't understand what you're talking about, although they shouldn't know the difference. Okay, so here is this aforementioned rule of extensionality. So we have a quantifier-free premise and we prove an equality. So here we just have depict this only for the base type. And like in yesterday, the equality between objects in, let's say, in the norm space is a defined notion. We actually represent the pseudo norm, and then we define equality by saying two things are equal if the norm distance is equal to 0. So that's actually a pi01 statement. And so you cannot in general claim that if things are equal, then the F makes them equal again. But if you have a proof of equalness, and the quantifier-free premise can have free variables, so it's actually the same as if you allow an existential premise. But if you have a universal premise, then there are counterexamples. Okay? So that's the rule we have. And full extensionality is an extremely strong principle. If you naively treat this, actually it invokes, as we will see in a minute when we consider set-valued operators, it implies that the operator is trivial. It's either the full operator or the empty operator. So there's no constructive way of treating full extensionality, but one can treat various special forms, and then this gives rise to special assumptions on A being sort of continuous in some Hausdorff sense and so on. All this occurs actually in the analytic literature. But for the time being, I just want to say this. So it's important to keep an eye on what type of extensionality you need, if at all. And sometimes you can involve subtle tricks to avoid extensionality. And of course, the analysts don't talk in this way, but they do exactly that. So they have a way of kind of, dream walking to avoid extensionality. And I want to explain. And so in order to know what type of extensionality you need, and if you need anything at all, I mean, this is a perspective of reverse mathematics. Does your actual statement imply some version of extensionality? Then, of course, you cannot do better than that. And then you have to face what quantitative assumption you have to make in order to interpret this amount of extensionality quantitatively. And this is particularly important when it comes to set-valued operators. And that's a topic in optimization where basically all operators are set-valued. And they are treated in the formal system. I mean, the first person who did this systematically was Nicholas Pischke in his PhD thesis. They are treated intentionally. So here a bit on these operators. Suppose you have a Banach space, and suppose you have a set-valued operator which you can identify with its graph, and then it's just a subset of x times x. And the domain is defined as those points x where a of x is non-empty, and then the range is the obvious thing. And an operator in Hilbert space is called monotone. Well, if it's monotone, so if you just are in the real line, this is just means monotone. Yeah? The scalar product just multiplication, and it just means monotone increasing. Yeah? And in Hilbert space, it means this. In Banach space, this notion can be also expressed, then it's called the operator, because there are different ways of doing this, resulting in completely different theories. But if you do it like this, then the operator is called accretive. And if the space is the Banach space, a Hilbert space, then being accretive and monotone are the same. Now comes, people use Thorne's lemma to say whenever you have a monotone alias accretive operator, you can maximally extend the graph so that you cannot make it strictly bigger and still maintain monotonicity. So then that's called maximal accretive. And the important theorem is due to Minty that if you are maximal monotone and you work in a Hilbert space, then identity plus A has full range. Okay? That's a consequence, and that's an if and only if. Okay? And in a Banach space, this is not true. Having full range implies that the operator, which is assumed to be accretive, is actually maximal accretive. But the other direction is not true. And so one actually defines M accretive not as maximally accretive, but as accretive and satisfying this. And that's the main obstacle in applying accretive operators to Cauchy problems, is to achieve actually this, or at least some weakened version, so-called range condition. So that's typically the hard part to actually establish this. In Hilbert space, you know it's automatic if the operator is maximal. Mm-hmm. I think it was Minty who, I don't know. I'm not an expert on this. Anyhow, it's, by the way, there are many ways, other people call it dissipative. The result is actually, an operator is accretive if minus A is dissipative. We have to be very careful in the classical work by Barbu from the 76. He always talks about these things, but he has a definition, everything A is minus A. Because for him, accretive is the same as dissipative. No, it's minus. We are in a vector space. I mean, you just take, when you have X and before Y was an A of X, now minus Y is an A. Okay, so now I treated originally abstract things intentionally, arbitrary convex subsets, for example. So you just make a characteristic function for that, which is of course completely non-constructive if it's going to be extensional, but who cares? You just hardwire this into the system, and then you state axioms if things are convex combination and the original points were in the set, then this is in set, that's a universal axiom, and it doesn't have problems, and so on. And in the same way, Pischke introduced in this JML paper monotone operators, and he said, well, actually in practice, we only need this, maximality is only needed to ensure this. So let's forget about maximality, just hardwire this into the formal system, and this you can actually do in a very elegant way. and using the so-called resolvent. We see this in a minute. So what he actually axiomatized is not maximality, but having this property. And then he did a piece of reverse mathematics for extensionality. So then you can actually show this part of Minty that this thing implies maximality. This is actually equivalent to the full extensionality. So full rangeness is a product of composition of being fully maximal and having extensionality. If you hardwire this and take this as your starting point, and if that's all what is needed, and the maximality was only used to achieve this, you have avoided this use of extensionality. So this is already what I said, and sometimes you cannot avoid full extensionality, but you don't need the naive version, which would completely trivialize the whole thing. So sometimes you do a partial extensionality of the thing, and then that results in a very natural form of, in a weak form of stating, I mean, in general, if the operator would not be set valued, then the full extensionality, if you make it quantitative, means the operator is uniformly continuous. Okay, so that's the general picture. So if you have some extensionality on the operator, not just on the characteristic functions, so in a more reasonable way, and then this triggers some sort of continuity. Now this operator is set valued, it triggers continuity in the Hausdorff sense, but it actually does in what is sufficient, and there are reasons logical for this is some weaker form, and intuitively we picked that weaker form in a paper and has been repeatedly used, and the work of Pischke shows why this is exactly good. So here again, I think some reverse mathematics, Pischke has lots of results in this recent paper in mathematical structures in computer science, relating various kinds of extensionality to various forms of maximality considered by analysts and so on. So here again, the intentional statement. So we represent the operator, the graph, by its characteristic function. So then being a zero of an operator, by the way, in optimization, people want to find zeros of operators. It's not the time today to talk about that, but you can translate the optimization problem, finding a minimizer of a lower semi-continuous proper convex function, and you take the subdifferential of that function, that's the maximum monotone operator, and then the zeros of that operator are the same than the minimizers of the function. So in that sense, finding zeros of operators is the same as minimizing functions, and that's why optimization people focus on that. Now, what is a zero of an operator? It means just that zero is in the range of Z. The other points which are not zero, but zero is among those. Now, this is a completely quantifier-free statement, so it doesn't have any computational content, it seems. But let's now make it extensional. Let's extensionalize this property. With extensionality in both arguments, of course, it's the same as saying there exist points V and W, which are in the graph of A, such that Z equals V and V equals 0. A crazy way of writing the same thing. But now you have proper quantifiers here, and if you write this in this way, then you can actually treat things quantitatively. This formula is now extensional in Z. And let's just spell out the quantifiers hidden here. There's a universal quantifier, so that's what this means. Now this suggests a notion, and this is exactly the right notion for the quantitative analysis. It's not straightforward why this should be the notion, of being an epsilon zero. Normally you say your point is an epsilon zero if the absolute value is smaller than epsilon. Here you say it's an epsilon zero if you are epsilon close to a point whose norm is epsilon. It's not even clear why this is then a real zero if this happens to be true for all epsilon, because you need the graph of A to be close to conclude this, but that follows if the operator is maximum. You see. Okay, so that's the right version. So now I come finally, that's the trick by which analysts play with extensionality without knowing, namely the resolvent. You can write the whole thing in a fully extensional way using the resolvent. The resolvent is a strange function here. So you have a set-valued map, you take the pre-image, this seemingly makes it even more set-valued, even if originally it would be single-valued. In general, if you take the pre-image, it's set-valued. But this set-valued is actually single-valued. So this is always single-valued. That's a consequence of monotonicity. And whereas the operator can be completely bad, the graph has absolutely no continuity or whatever behavior. So that's why it's called non-smooth analysis. This function is beautiful. It's a Lipschitz 1 function. Okay. And the defining axiom is this one here. This is what Pischke used as an axiom. And in the formal system, the operators are always by design total. And so you actually express that this resolvent is total. So you actually express that this is a full space. And in this way, you by the very type system, you impose that the operator is maximal without taking that. Okay. And now the basic fact is this seemingly intentional thing here is the same as this extensional thing. On the right-hand side, we have full extensionality. We have a continuous, uniformly continuous function. This is, of course, as extensional as it gets. The formal system can prove that this is extensional. And on the left-hand side, we have an operator. The result cannot prove anything about extensionality. And we have that the zeros coincide with the fixed points of this thing. Now you can play back and forth. You can play fixed point arguments. You go back to the zero set. You import them into the fixed point arguments. And that's what these people do. And you have to do it in a very subtle way in order not to trap into an extensionality issue, which you cannot quantitatively solve. And they somehow avoid this. Okay, and let's look into the proof. Okay, let's look in. Okay, let's actually. So, logical obstacles to. Now we want to make a quantitative form of this. We want to say if you are a delta approximate fixed point, then you're an epsilon 0, and if you're a delta 0, you're an epsilon fixed point. You cannot do because there is no epsilon. That is a quantifier-free statement. Doesn't make any sense. But if you use the aforementioned extensionalized version, this actually makes sense. So in the first you cannot make, this is a pi 0,1, the other one is quantifier-free. There's no way to say how much of your pi 1 statement do you need to prove your quantifier-free statement. The quantifier is a full statement, and a weakened version of pi 0,1 doesn't apply the pi 0,1. But if you take the extensionalized version, it works. So that's this solution, and you have to take it exactly as this. And here's the result. It's very simple. If you have an epsilon third approximate 0 in the aforementioned sense, then this is an epsilon approximate fixed point of the resolvent. And in the other direction, it is even with the identity. But in one direction, actually in this one here, you actually need the operator to be maximal monotone, only for this one here. How does this go? This is the only proof I have here. So suppose you have an epsilon third approximate 0. This means exactly this. There are these points in the graph. You are epsilon third close to this, the z, and the thing is not 0, but the norm is smaller than epsilon third. Now, because of this thing here, we clearly get this thing here. V plus W is in identity plus A of V, because W is in A of V and V is in I of V. Now, since this is single valued, so this is a point in here. But since it's single valued, it has to be this point. But this point is defined to be the resolvent. Now we use, so far we haven't used the maximality, but now we use the maximality. By the maximality, the resolvent is total. And so we can apply the resolvent not only to this point, which we can by definition, but we can also apply to this point, which is not clear in the beginning, but if it's total, we can. And then we use the non-expensivity, the Lipschitz 1 property of the resolvent, and we get immediately this approximate. And then just adding the errors, we get for the original point z, we are actually interested in this z is an epsilon. And for the other direction, it's even simpler. By the way, this is actually, in a way, you can view this statement here as an intentional certificate for the fact that a fixed point of J must be a 0. If X is a fixed point of J, then this is 0. But if X is a fixed point of J, this is X. So 0 is an X. And we have used twice extensionality. This is a way of stating the same thing without using extensionality. You have to use that version, and that's what the analysts do. Good. So now we have this. And now you can finally conclude that if the operator is maximally monotone and Z is an epsilon approximates 0 for all epsilon, then it's actually a 0. For that, you need extensionality, but only for the verification of that fact. Why is that the case? Well, we just proved if you are for all epsilon 0, then you're for all epsilon an epsilon fixed point for JA, because it's epsilon third, it doesn't matter. But if you're a fixed point for every epsilon, then you're a fixed point. On that side, the statement is clear. But if you're a fixed point, by extensionality, you are a 0. So you are a 0. And that's not a miracle, but because we use the maximality of the operator, because we use the totality of the resolvent, and that implies that the graph is closed. And that's exactly what is needed in this. Okay, now here's, I talked about many times about this example. It's my favorite proof mining example, because it satisfies the gold standard. It's a deep result. The proof is completely non-effective. And you get a full rate of convergence, not just some strange thing, no meter stability or so, and the rate is a polynomial, so it couldn't be better. So here is the famous solution of Bauschke's so-called zero displacement conjecture. So you have a Hilbert space, you have finitely many closed convex subsets. You project to those, you take the cyclic projection algorithm, you take the whole package of successive projections, and then you iterate that. And that is, as the people say, asymptotically regular. So this tends to 0. So this has been studied already by von Neumann and in many special cases over the years, but it was proven in full by Bauschke, and he uses this whole approach of maximum monotone operators to do that. And it follows from logical meter theorems. We don't have the time today to say there must be a rate of convergence for this, and it only depends on 4 data, on the epsilon, on the number of the sets, on the bound, on the norm of the starting point, and on bounds on the norms of some elements you can pick of your set Ci. If you know for at least one point in each set a norm upper bound, that's sufficient. Now, the proof uses that metric projections are firmly non-expansive, and firmly non-expansive mappings are resolvents of maximum monotone operators. So that's the and then we use stuff about approximate fixed points for firmly non-expansive maps to convert this into approximate zeros of the operator. Then we need an operator argument due to Brisis and Harut to quantitatively analyze, and then we translate things back into the fixed point world, because the statement itself doesn't mention any operator, right? And then we use that's another thing which is a different kind. Firmly non-expansive maps are not closed under composition, but a slightly more general notion of strongly non-expansive is, and that's all what is needed. Anyhow, here is then the promised rate, and it's a polynomial in all 4. Okay. This has been generalized to averaged maps by Andrei Siposh, and most recently even to super strongly non-expansive mappings. In this case, even the original convergence wasn't known before. So even the convergence for the first time, or the quantitative convergence. So here's another thing. As I mentioned, there are algorithms and people care about computing zeros of operators. The most basic algorithm is the proximal point algorithm. You just iterate the resolvent along certain colors, which you have to choose here. And and that at least weakly converges, and there are also versions which strongly converge and so on. But the problem is that it's very complicated to compute the resolvent, because to compute the resolvent explicitly, one has to solve an inverse problem. And so there's a whole literature of virtually hundreds, if not thousands, of papers which come under the name of splitting arguments. So if it happens that your operator you are interested in can be split into the sum of two operators, which are more manageable, and such that for each of its components you can compute the resolvent, then you are in a better position. And so people try to design algorithms and it works, and one is the famous Zeng's algorithm, where here one operator is essentially single valued, and for the other you use the resolvent, but you don't need the resolvent for the sum. You have this algorithm, and this converges then to a zero of actually the sum. And if the operator is not just monotone, but uniformly monotone, you have a distance from zero, and this only depends on norm bounds, then the operator is called uniformly monotone. Then you can make this into strong convergence, and then the zero is actually unique. Okay, so when we analyze this, an important property is a so-called Ferré monotonicity property. With respect to the solution set, you have this property here. Now, one wants to use a macro, which we did with Loistian and Nicolai in 2018. If you have a quantitative version of this Ferré business, then you can actually do things. Quantitative means if you just want to have this up to an error epsilon, then you only need a delta approximate zero. Can you get this here? Well, it depends on how do you define a delta approximate zero. If you define it in this way, as I had indicated, then in fact you can do. This is a recent paper by Nicholas again, and otherwise you can't. And then you actually get a rate of metastability in the finite dimensional case. In the finite dimensional case, we only have weak convergence, so strong convergence, and there are counterexamples to strong convergence, so you need finite dimensionalness. But in that case, you get a rate of metastability, and you have this result. By the way, this is a finitistic certificate of the following result, which is the original result. Xi and Zi both converge to a zero of A plus B and to the same zero. That's the original statement. Now, if you just throw away here this counter function, you get, of course, a Cauchy property. It's just a one-line argument with classical logic. If you then apply arithmetic comprehension to get the limits, you know that this converges and this converges with the same limit. And you get, if this holds for all epsilon, you get that the limit must be a fixed point of the resolvent of A plus B, but by extensionality, this means it's a zero. So if you take this result, you add extensionality, you add classical logic, and you add arithmetic comprehension, you get, just with a magic stick, you touch the result. You don't have to do any mathematics, you get the original result. So for all intents and purposes, this covers the original result, but in a finitistic way. That's what I'm saying here. Okay. Further results. As I mentioned, if this is uniformly monotone, then one can actually get a rate of convergence. This is a paper of myself and at that time bachelor student of mine. It doesn't happen that often that the bachelor is in journal publication. And then really much generalizes. I gave a talk on this in the presence of an optimization person, actually from Vienna, Radu Botz, and he said, yeah, okay, this is all fine and good, but now people do this type of thing. Can you do that? So actually, we wanted to. He sent us a paper by these two people about a very thing, and then we looked into this and we saw, aha, for all intents and purposes. It can be reduced. I mean, that's what they actually do, is to reduce this to this thing, to the original Zeng, but with error terms and with a bit more general. So we upgraded this analysis to this situation, and then we inferred this, and modulo minor revisions. This is now a paper. Okay, so that if we could do this within a couple of weeks. So Radobot said this in early September last year to us, and in late September I gave a talk in Vienna when the Yellow Ring Award ceremony was, and I announced in his presence already this result. This can be done. Okay. Now a completely different topic about Cauchy problems. So I hope. So this is a second order PDE, and A is an accretive operator. Many abstract Cauchy problems can be written in this way. For example, by the way, the Navier-Stokes equation can be written as a PDE. So this is here a second order, for obvious reasons, Cauchy problem, and people are interested in analysis. Now it has been studied by Pedro Pinto and Nicolas Pischke in the first order case, so where P is 0, and a bit more special R in the first order case. And this is a paper in Documenta Mathematica, where full quantitative analysis of how the solutions behave asymptotically and so on works. Then Nicolas treated the homogeneous second order case in the special situation where the first order part is actually trivial. So you only have the second order part, but not the first order part, and the F is not there. The F is constant 0. That's the so-called homogeneous case. And very recently, Shahram Zaidi from Iran, from the University of Kurdistan, he's been visiting Darmstadt. He's an expert on these subjects. He studied the full second order problem, but we first focus on a discrete version. Then this becomes the so-called difference inclusion. And that we fully solved, but it's now ongoing work to do the full. So why I'm saying this, because we come to an extensionality issue. So the discretized version gives rise to this type of iterative procedure of sequence UI. This is standard way, it's so-called forward-backward Euler approximation. Anyhow, the solution of existence of all this stuff is based on a classical paper of Pesi, who imposed a so-called condition. It's a very logically involved condition, the convergence condition. And Pinto and Pischke gave quantitative versions of that and then expressed the results in terms of moduli witnessing these quantitative versions. Now, in recent work with Zaidi on the second order difference equations, a much more liberal form of convergence condition came up with weaker modulus, and we have a result in it. But now I want to explain this modulus in logical terms. How can this modulus be motivated? So the condition which Zaidi came up with actually is the following. So you have a non-linear set-valued operator and a Banach space, and it has a 0. Then if this here happens, you say the convergence condition holds. So that's pi3 implies pi3. Convergence implies convergence, but you can convert this into a for all exists epsilon delta statement, namely this one here. And then it's natural to ask, it's uniform in the sense this exists is in front of these universal quantifiers. So it's often natural to ask, what is the original statement of which this is the uniformization of? For example, take Pesi's definition of a convergence condition. It also can be written in this way, and you get the pre-uniformized version. That's also an important notion which is studied in the literature. Let's see what this notion here is. You get this one here. Just convert the quantifier. So I'm just saying instead of exist for all, I say for all. You know, right, what this means? I mean, if you pull the quantifiers here inside, you get a for all n here. So it just means y is 0. And this just means the distance here is 0. So with extensionality, it just means this. And this is a weaker form of saying 0 is an x. So you actually say it's just the closure. So it's A implies A. Weakening of A implies A. So how can a uniformized version of A implies A be of interest? Well, because here there are no quantifiers. But if you extensionalize the statement and you get quantifiers, then all of a sudden gets a meaningful statement. And then to say that these quantifiers behave uniform, this is a strong statement. So let's see, using extensionality being 0 can be written either in this way. I use partial extensionality. I now use extensionality in the first argument of A. I'm sorry, in the second argument of A. I can also write it using extensionality in the first argument of A, like this. And now I state that the one partial extensional version implies the other partial. So if it's extensional on one, it's extensional in the other. Now it's already a non-trivial statement. Now I weaken this extensional statement to its epsilon version. And if you then take this, implies this, pre-next, you get exactly this statement here. So this is nothing else but saying that a special form of extensionality implies another special form of extensionality. Okay, and so then we make this, of course, a modulus. So if we have this witness, we call this a modulus. And now why is this whole notion of interest? Because in this notion, you can solve the problem. You get a rate of convergence for this. You suppose you have a solution UN for this problem, then it converges in sequence converges with this rate of convergence. And that rate involves this modulus omega. So, but this modulus omega can otherwise be hardly motivated for, except for by this extensionality reasoning. So I think what the proof actually needs is a special form of relations between two kinds of extensionalizing partially A. And we have to make that quantitative. That is not guaranteed because we cannot prove that in our system. So that's a proper condition. So we make this a definition. We say this is the case, and we have a modulus that is not obtained by proof mining. That's assumed as an assumption, but this is a meaningful assumption because in many cases, and we have studied, for example, the finite dimensional, there's all that exists and so on. So in many cases, it actually exists, whereas the extensionality in full to uniformize renders the operator to be the trivial operator, either empty or full. Now empty it cannot be because it's 0, so it has to be full. So it's a complete trivial statement. But looking into the specialized form. Okay, here's another final specialized form. This is a bit older, but it fits into this topic. Often in analysis, you use extensionality in this form. So you have a solution of some problem. Let's say a fixed point problem or 0 problem or whatever. You have a solution, and then some other point is equal to your solution, and then it's also a solution. This is clearly extensionality. You cannot prove this by the extensionality rule, but it's not full extensionality because one of the two components is not an arbitrary point, but it's a solution. Let's see what happens if you want to make this quantitative. If you want to make this quantitative, it means if you want to get the conclusion to be an approximate fixed point, well, then it suffices that P is an approximate fixed point and that X and P are approximately close. There are two data here, and exist this for all and this for all pop out as exist. So they are witnessed in terms of delta and in omega, and that's what we defined. And we call in this paper with Leostian and Nicolai, we call this modulus for uniform closeness. Called like this because it is a form expressing the closeness. Okay, anyhow, that's what it is. Now, if the operator is uniformly continuous, I mean, if it's uniformly continuous, then you get a witness for the extensionality. So you should actually get a witness for the special form of extensionality, and you actually get. If you have a modulus of uniform continuity, then these moduli can be nicely produced. But the point is, the moduli can be also nicely produced for discontinuous functions. So you have a discontinuous function, You use extensionality, and does not mean that you have to impose that the functions are continuous in order to move on. No, you just do this. And this actually has been done by analysts in special cases. So there is a cryptical condition E generalizing a condition C of Suzuki by Garcia Falset, and the condition says as follows. Map satisfies the condition E if there is a mu such that this holds. And now you see, this just says in a very special, it's a kind of Lipschitz-Hölder way of saying we have moduli of being uniformly closed. Yeah? Because if now this is an approximate fixed point, and if you approximate closed, then this is also approximate closed. So this is, but it's in terms of, it's actually kind of Lipschitz version. Yeah, there's also Lipschitz-Hölder version. Lipschitz version of, so in this case, you just get therefore a linear modulus. So the analysts intuitively realized it's better to remember that we use extensionality only in a special form. And this has discontinuous witnesses. For example, take this function here. This is completely discontinuous at x equals 1, but it satisfies the condition E, mu being 3. Okay, so that is, we have many results on this paper, and that's thank you. Yeah. No. Exactly the latter. Yeah, because I mean you have the same phenomenon again in with ultra products. So when is an ultra product separable? Only if it's finite dimensional. So because the uniform quantitative version of separability is total boundedness. I mean, if separability just means restricted to, let's say, a bounded ball, means for every epsilon, you have these family of countable many points, one of which will be for every x epsilon close to your given x. You now say this index n is uniformly bounded, then it means you just need finitely many of those. So this is a net of total boundedness. So the uniform version, and in the ultra product, things get automatically uniform. In our version, it gets uniform because we use a monotone functional interpretation, which imposes that. Separability translates into total boundedness. So if the unit ball in a Banach space is totally bounded, then of course it's compact, and therefore it has to be finite. That's the reason. And the very separability is the counterexample. If you hardwire into your system, you have access to this countable representation. You can state the very separability as a property. And if you state that, and now you say, the Kohlenbach claimed as a meter theorem, let's apply Kohlenbach's theorem, you conclude that your space is compact and finite dimensional, therefore. This is completely false. See, this is already false in the very beginning. I mean, even the defining axiom is itself a counterexample. The point is, that's the only counterexample. If you define the space in this way, well, that's your problem. But if the statement didn't say anything about this, the statement said, let X be in Banach space. So it's not about, even if you only want this, the only Banach space you're ever interested is L2, not to use that it's separable gives you a bound which you could not guarantee to get if you had smuggled into your system. Because if you give more information about your space being separable, you can prove more theorems about the space, and you can prove theorems for which this is false, whereas what you want to prove should be true. So how can you distinguish the two? Only if you have a formal framework which supports to keep track of whether you use separability or you did not. And it's the same also, why do you want to have a weakly extensional system? Because only if you have a framework where you can monitor whether you used extensionality, and in case yes, how much of that, you can actually draw a conclusion about this. It's like if you want to investigate, the amount of action of choice involved in the maximal ideal theorem, you have to work over ZF, not over ZFZ. So if you want to calibrate the amount of choice, if you want to calibrate the amount of separability, you have to work in a system without separability. If you want to calibrate the amount of extensionality. And so it's exactly this point here. That's why it's completely misleading what these foundationalists say is avoiding pseudo-generality. No, they avoid examples, they avoid applications, not pseudo-generality. That's what they avoid. They avoid applications, Bishop, Pfefferman, Martin Löw, all these frameworks, Simpson, Friedman. Well, yeah, sure. I mean, if you have an ultra product of a Banach space again a Banach space, and you can ask when is that separable? And it turns out only if it's finite dimensional. But I'm not an expert on this, but last time I looked into this, I seem to remember this was a result. Actually, we have for all these, actually, you can make this. Right. And that's, by the way, why they use ultra products in the first place, because how are ultra products used in fixed point theory? You get a sequence of approximate fixed points. In general, these operators don't have fixed points, counterexamples, because of lack of compactness. But you go to an ultra product, then in an ultra product, you have actually a fixed point. Yeah. Yeah. I'm saying it's not separable. Yeah, I mean, but no. You have to, if you have a finite dimensional, I think that's. I mean, I'm not an expert on this. If you have a finite dimensional Rn, and you take the ultra product, then that should be. Yeah. Yeah. Anyhow, I mean, I'm definitely know for sure that if it's separable, then it has to be finite dimensional. By the way, you can make these beta theorems. They're a kind of rule. If you prove some non-uniform result, you extract a bound on the uniform, you can make this an implication. Let's just say if something is non-uniform, then it's also uniform. I call it uniform boundedness principle. It's a classically false principle, but you can add it and it's conservative for a nice class. This exactly mimics the use of ultra products, because then you can prove the same thing using, for example, uniform boundedness. You can prove that every space is complete. But suppose the metric space would be incomplete, then it had to be uniformly incomplete, but you can immediately say this is an inconsistent notion. And in fact, a Banach and an ultra product is always complete. Ultra product metric space always complete. And you have, if you are separable, then you are totally bounded. Again, you are finite dimensional. That's exactly. If you are strictly normed space, then you are already uniformly convex. If you are smooth, then you are uniformly smooth. So all these things, these uniformizations, are in fact consequences of this uniform boundedness result. And sometimes it's useful actually to use this also in proof mining. You just pretend this is the case, and then if what you prove is in this class of statements where you can eliminate the use of uniform boundedness, then you're proven. And that's, I mean, what the people do in actually the functional analysts do. They don't need logicians for this. They use this all the time. If you want to show that an algorithm is Cauchy, but you badly need that the operator has a fixed point. Unfortunately, it doesn't. So you go to an ultra product, you extend your non-expansive map to that. That has a fixed point. Then you perform an argument. You get that your sequence is Cauchy. But the Cauchy statement is actually, it's a first order statement, so it's actually also true in the original setting. So you have proven that. I mean, speaking